Hello and welcome back to the Sleep Science Space. I'm really glad you found your way here tonight. Maybe your day has been full and heavy, or maybe you're simply someone who likes to fall asleep with the universe drifting quietly in the background, stars, galaxies, and all the soft mysteries that live between them. Either way, this moment is yours. You don't need to do anything now. Just settle in. Let your body loosen. Let your breathing slow and let your thoughts drift like dust moving through starlight. Because tonight we're taking a gentle journey across the cosmos, not just a single star system or galaxy, but the vast unfolding universe itself. We'll wander softly from one idea to the next, touching on black holes, ancient light, dark matter, invisible worlds, and cosmic riddles that astronomers are still trying to solve. Some details may spark wonder, others may settle into your mind like a quiet echo at the edge of sleep. And if these calm explorations help you relax, feel free to like the video or subscribe. It helps others discover this peaceful corner of the universe too. Now, when you're ready, let's begin. The universe might be older than we think. For many years, scientists have placed the age of the universe at about 13.8 billion years, based on how fast space is expanding and the faint afterglow left behind from the Big Bang, the cosmic microwave background. But as our tools have improved, a few measurements no longer line up perfectly. Some extremely old stars appear at first glance to be older than the universe itself. Certain galaxies seem too mature for the timeline we use. And some physicists wonder whether dark energy, the force driving the expansion, might be changing over time. Most astronomers still agree on the 13.8 billion year estimate. But the tension is interesting. It hints that our picture of the early universe may be incomplete, as if the beginning we talk about was only one chapter in a much longer, more complicated story. Thousands of planets drift through space with no star at all. We often imagine planets as loyal companions to stars, but not at all worlds have a sun to orbit. Some planets travel completely alone, unbound, silent wandering through the galaxy in total darkness. These rogue planets might have been born around stars and later flung away by gravitational chaos, or they may have formed on their own like tiny failed stars. Most are nearly impossible to see revealed only when they briefly pass in front of distant starlight or give off a faint warmth in infrared, and they may be astonishingly common. Some scientists think there could be more rogue planets in the Milky Way than stars themselves. Imagine that billions of lonely worlds drifting endlessly through black starless space. No dawn, no dusk, just a quiet, eternal night pierced by distant constellations. The universe may renew itself in endless cycles. In the most familiar model, everything begins with the Big Bang and expands outward forever, gradually cooling as galaxies drift apart. But other theories offer a different rhythm, one where the universe expands, then contracts, then expands again, in a repeating cosmic heartbeat. In these cyclic universe models, the cosmos might collapse inward after trillions of years, then rebound into a new expansion. Each cycle wipes away the old galaxies and stars, but may leave faint clues of previous universes imprinted in the next. We don't know if this is how reality works, but the idea is captivating: a universe without a true beginning or final end, just an endless rising and falling creation, transformation, renewal across unimaginable eras of time. So, the oldest light we can see is from 380,000 years after the Big Bang. Before that moment, the early universe was nothing but a blazing, swirling fog, so dense and energetic that light couldn't travel more than a tiny step before scattering again. Photons bounced endlessly, trapped in a storm of charged particles. But as space continued to stretch and cool, everything reached a quiet turning point. Atoms finally formed. The fog thinned, and for the first time, light slipped free and began its long, uninterrupted journey. That ancient radiation is what we now call the cosmic microwave background. It isn't the glow of stars or galaxies, it's the universe's first clear breath, released when it was only about 380,000 years old. Those photons have been moving ever since, stretched thinner and colder over more than 13 billion years as space expanded around them. Today, they reach us as a faint microwave whisper, a soft afterglow that fills the entire sky. It is the oldest message we can still read, a quiet remnant from the universe's earliest moment of clarity. Some stars host planets made almost entirely of diamond. In a few rare corners of the cosmos, planetary chemistry takes a dramatic turn. If a forming world contains far more carbon than oxygen, and the pressures deep inside rise high enough, an astonishing transformation can occur. The entire planet may crystallize into diamond. Astronomers have already found at least one strong candidate: a dense world orbiting a dead star, known as a pulsar. Based on its extreme density and composition, the planet may be a massive carbon crystal, hot, dark, and nothing like a gemstone, but still built from kilometer deep diamond lattices. These exotic worlds are uncommon, but they show just how creative the universe can be. Some planets are oceans and rock, some are gas and storms, and a rare few may be made of crystal forged under unimaginable pressure. Tomorrow, the universe may have no edge, just endless curvature. It's natural to picture the universe as a giant sphere with a border somewhere far away. But everything we've learned so far suggests that space doesn't have a hard boundary at all. According to Einstein's relativity, matter and energy determine the shape of the cosmos, and current measurements point toward a universe that is either truly infinite or so large and gently curved that it loops back on itself. If that's correct, then traveling straight ahead might eventually bring you back to your starting point, not because you hit a wall, but because space bends around on cosmic scales. Like walking around Earth, you'd never encounter an edge, only the continuous surface of a much larger, more subtle shape. The universe may not be endless in size, but it may be endless in direction, an infinite path without a boundary. The sun may have had a sibling, and it might still be out there. Stars rarely form alone, They tend to be born in clusters, siblings condensed from the same giant cloud of gas and dust. Many astronomers believe our sun once had a twin that emerged beside it over 4.5 billion years ago. If so, the two stars would have slowly drifted apart as the Milky Way's gravitational tides pulled their orbits in different directions. This hypothetical companion, sometimes nicknamed Nemesis, has never been found, and there's no evidence linking it to extinction events on Earth. But the idea remains scientifically plausible, a lost sibling of our Sun wandering somewhere along a distant galactic orbit, glowing quietly in the vastness of space. The sky we see today may be missing a star that once shared our birthplace. So, a single raindrop of neutron star matter would outweigh Mount Everest. Neutron stars are what remain after a massive star collapses in a supernova. They are tiny, barely 20 kilometers across, but their gravity crushes matter to unimaginable density. Inside a neutron star, atoms no longer exist in their familiar form. Electrons and protons merge into neutrons, packed so tightly that a teaspoon of this material would weigh billions of tons. To imagine a droplet of neutron star matter is to imagine the heaviest substance nature can create, so dense that even a fragment smaller than a raindrop would outweigh entire mountain ranges. In every sense, neutron stars are cosmic extremes, small, fierce, and forged in the final breaths of dying suns. If you imagined a single raindrop of neutron star material resting on your hand, it would outweigh every mountain on Earth combined. That level of density is far beyond anything we can picture in the everyday world. Inside a neutron star, atoms no longer behave like atoms at all. Their structures collapse inward until electrons and protons fuse into neutrons, forming a supercompressed, superfluid ocean of matter. These stars are tiny, dark, and impossibly heavy. Many spin dozens or even hundreds of times per second. Yet, for all their violence and speed, they represent a final still moment in the life of a once massive star, a place where matter becomes gravity and gravity becomes almost everything. Ooh. Light from one galaxy can reach us from multiple directions. In the deep fabric of space-time, light is not always free to travel straight. Massive galaxy clusters create regions where space-time curves like a lens. When light from a distant galaxy passes through this warped region, it bends sometimes gently, sometimes dramatically. Because of this, we can see multiple images of the same galaxy arriving from different paths around the warped space. They appear as glowing arcs, stretched smudges, or even perfect rings. These are not copies scattered across the universe. They're simply different routes the same ancient light has taken to reach us. In rare and beautiful cases, astronomers have even watched the same supernova explode more than once its delayed light, looping around the curvature of space-time. A quiet reminder that even photons can wander, take detours, become lost, and still eventually arrive. But the first stars may have burned a million times brighter than the sun. The earliest stars were not like the ones we see twinkling today. Formed from the pristine hydrogen and helium left behind by the Big Bang, these population 3 stars grew enormous, some hundreds of times the Sun's mass. With no heavier elements to cool them, they ignited fiercely, burning through their fuel quickly and brilliantly. For a brief cosmic moment, they shone a million times brighter than our Sun. Their lives were short, just a few million years, but their influence was permanent. When these giants collapsed, their supernovae forged the first heavy elements: carbon, oxygen, iron, the ingredients needed for planets, oceans, and eventually life. Though none survive today, their fingerprints remain in the chemistry of ancient gas clouds, the quiet echoes of a universe learning how to build itself. Sarasembutsu topo bukes asaiches. The symbol today Simpus so suk so up is that sound. So dark matter streams through your body as you sleep. Right now, as you lie still, something unseen is passing through you, quiet, invisible, and constant. Dark matter doesn't shine, doesn't collide, and doesn't leave a mark. But it has gravity, and this gravity shapes galaxies and cosmic structures on the largest scales. Our Milky Way drifts inside a vast halo of dark matter, and as Earth moves through that halo, trillions of dark matter particles pass through every square centimeter of your body each second. You don't feel them. You don't hear them. They simply drift ghost like through atoms and empty space. Without dark matter, galaxies would fall apart, stars wouldn't gather into spirals, and the universe would be a very different place. We still don't know what dark matter is, but its quiet presence surrounds you even in the moments when you're drifting toward sleep. Whoa, ho. Some galaxies glow without any stars inside. Far from the bright spirals and glowing clusters we normally imagine, astronomers have discovered galaxies that shine faintly while containing almost no stars at all. These ghost galaxies are rich in dark matter and gas, yet somehow never ignited into stellar birth or lost their stars long ago in violent gravitational encounters. A few are barely detectable, revealed only in specific wavelengths as dim smudges on deep sky surveys. Their silence challenges our understanding of how galaxies form. If they contain so much dark matter, why did star formation stall? If they once had stars, where did those stars go? These pale drifting systems move through space like forgotten structures, quiet remnants of cosmic chapters we still don't fully understand. The universe has a cold spot that shouldn't exist. In the cosmic microwave background, the faint afterglow of the early universe, there's a region noticeably colder than the rest. It's vast, spanning hundreds of millions of light years, and its temperature dips more than expected from normal random variations. Some scientists believe it may be an imprint from the early universe. Others think it could be a void, an enormous region of space with far fewer galaxies than average. And some theories push further, suggesting it might hint at something even stranger, perhaps a collision between our universe and another in the distant past. No explanation fits perfectly. The cold spot remains one of the quiet mysteries resting in the background of everything we see, a subtle anomaly left over from the dawn of time. In the cosmic microwave background, the faint ancient glow left behind by the Big Bang, there is a patch of sky that behaves differently from the rest. A region colder, larger, and more pronounced than any simple fluctuation should be. It stretches across hundreds of millions of light years, an enormous shadow on the oldest map of the universe. According to the usual rules of early universe physics, such a feature shouldn't stand out so sharply, yet it does. Some astronomers think this may be the imprint of a cosmic void so vast that its emptiness subtly cools the passing light. Others consider a stranger possibility that in the first fractions of a second after the Big Bang, our universe pose might have brushed against another, leaving a faint fingerprint behind. No explanation fits neatly. The cold spot remains a quiet, persistent puzzle, a soft reminder that even after decades of study, the universe still keeps secrets tucked beneath its oldest light.
Chatham.
The moon is slowly leaving us behind. Each year, the moon drifts about 3.5 centimeters farther from Earth, so slowly you'd never notice, yet so steadily that the effect accumulates across time. Billions of years ago, the moon was much closer, looming large in Earth's sky, while a single day lasted only a few hours. The cause of this slow escape is tidal friction. As Earth spins and the moon pulls on our oceans, a tiny transfer of energy pushes the moon outward in its orbit. It's a quiet, patient process, one heartbeat of distance added every year. Far in the future, Earth and the moon may settle into a mutual stillness, each one perpetually showing the same face to the other. For now, the moon simply drifts away millimeter by millimeter while we continue turning beneath its gentle silver glow. So, binary stars can exchange their outer layers like dancers in contact. In some star systems, two stars orbit so closely that their outer layers begin to blend together. As one star expands with age, its atmosphere can spill toward its partner, creating a swirling bridge of gas that flows between them. Sometimes the exchange is calm and steady, like a slow cosmic waltz. Other times, it triggers bursts of brightness, sudden rotations, or even the merging of the two stars into a single brilliant body. One star may become stripped down to a glowing core, while the other becomes swollen and enriched, reshaped by what it receives. Many of the universe's rarest objects, including certain supernova types and tightly bound neutron star pairs, begin their lives as these touching binaries. A reminder that even stars can share surrender and transform through the quiet pull of companionship. As eton. The vacuum of space is not truly empty. Even in the deepest stretches of space, where no stars shine and no particles drift, the universe never reaches true emptiness. Quantum physics tells us that the vacuum is alive with flickering activity, virtual particle pairs appearing and disappearing faster than any clock could measure. These quantum fluctuations fill every cubic centimeter of space, a constant whisper beneath reality. Though fleeting, they exert real influence. They push on particles' shape fields and contribute to the mysterious energy that fills the cosmos. This subtle background may even help explain dark energy, the force accelerating the expansion of the universe, stretching space time itself apart. In the stillness between galaxies, in the silence between stars, the universe is quietly active, humming with tiny bursts of creation and disappearance. Nothingness, it turns out, is never truly nothing at all. So when we picture deep space as silent and still, that image is only partly true. Beneath the quiet lies a dance of probabilities, a hidden shimmer of creation and disappearance, moments so brief and delicate that they exist only as possibilities before fading back into the void. Even in what we call nothing, the universe is busy, restless, quietly alive. But time may flow at different rates in different regions of the cosmos. We often imagine time as a steady river flowing calmly and uniformly everywhere. But in reality, time is woven into the fabric of space time, and space time bends. Where gravity is strong near black holes, neutron stars, or dense galaxy clusters, time itself slows down. Clocks tick more slowly. Moments stretch. This isn't speculation. Atomic clocks on satellites, just a few hundred kilometers above Earth, already experience time differently than clocks on the ground. Some cosmologists wonder whether time might also vary on enormous cosmic scales. If the universe expanded unevenly in its earliest moments, then different regions might experience subtly different flows of time even now. It's a strange idea, but in a cosmos governed by relativity, strangeness is normal. Time may not be absolute. It may stretch, bend, or drift quietly, shaped by the space through which it flows. Church boys who so just so said the Milky Way has a hidden halo far larger than the visible galaxy. When we picture the Milky Way, we imagine the bright spiral, glowing arms, swirling dust lanes, newborn stars. But this luminous disk is only the center of something far more expansive. Surrounding the galaxy is a massive ghost like halo of gas, ancient star clusters, wandering stars, and most of all, dark matter. It extends many times farther than the visible galaxy, forming a vast sphere that cradles everything we see. We can't observe this halo directly, but its gravity reveals its presence. Stars move faster than they should. Light bends subtly as it passes. Space curves where nothing appears to exist. The Milky Way, we know our entire sky, is just the bright heart of a much larger invisible structure wrapped around us in silence. So, uh, we've detected light from a galaxy born just 200 million years after the Big Bang. Thanks to the James Webb Space Telescope, astronomers have identified light from a galaxy that formed incredibly early when the universe was still young, still glowing with leftover heat. That ancient light has traveled for more than 13.5 billion years across expanding space to reach us. The galaxy itself is tiny, faint, and primitive, a fragile pioneer in the newborn universe. Observing it is like peering through a narrow window into cosmic childhood, a time when the first stars were just beginning to ignite, pushing back the darkness one spark at a time. Whoa. The large scale structure of the universe looks eerily like a neural network. When astronomers map millions of galaxies across the cosmos, a breathtaking pattern emerges: the cosmic web. Galaxies gather along enormous filaments. Vast, empty voids stretch between them. Dense clusters form glowing nodes where hundreds or thousands of galaxies intersect. Zoomed out far enough, this web looks uncannily similar to a neural network in the human brain. Galaxies as neurons, filaments as axons, cosmic voids like the spaces between thoughts. It's not a sign of consciousness, just a curious echo of structure across unimaginable scales. Still, it's quietly beautiful to think that the largest pattern we know, and the one inside your mind, shaped by entirely different physics, can end up looking so strangely alike. Stars can sing through the vacuum of space. There's no air in space, so you can't hear sound the way you hear it on Earth. But deep inside, stars' pressure waves ripple and bounce through their hot plasma, much like seismic waves inside a planet. These vibrations cause tiny pulses in the star's brightness and movement. By observing these subtle variations, scientists can listen to stars in a field called stereoseismology. Each star has its own rhythm, its own quiet signature. Some pulse quickly, others hum slowly with deep resonant tones that would take hours to complete a single cycle. These stellar songs never reach our ears, but they tell us what lies inside, revealing hidden layers, densities, temperatures, and ancient histories written in vibration. Literally, the seismology of stars. Each star vibrates with its own internal frequencies, a kind of celestial fingerprint shaped by its size, its temperature, its age, and the layers hidden beneath its glowing surface. By listening to these vibrations, these tiny shifts in brightness and rhythm, astronomers can peer inside a star the way doctors use ultrasound to look inside the human body. It becomes a kind of cosmic echolocation, a way to hear the music of stars across unimaginable distances, even if the song is forever silent to human ears. In those soft, slow pulses is a map of a star's soul, its past, its present, and even its future. Some stars are older than the galaxies they live in. Galaxies are not born fully formed. They grow slowly over time, gathering smaller systems, merging with wandering clusters, and absorbing stars that once belonged to entirely different homes. Because of this, some of the stars inside a galaxy today are far older than the galaxy's current structure. These ancient stars often live in the outskirts in the galactic halo or inside globular clusters, tightly packed balls of stars that orbit like distant lanterns. Some of them are over 13 billion years old, nearly as old as the universe itself. Their chemistry reveals their age. They contain almost no heavy elements, only the simple atoms forged in the earliest moments of the cosmos. They shine with a faint, pristine light, carrying stories from a time before galaxies had spirals before planets existed, before the universe grew rich and complex. They are cosmic fossils, quiet, enduring witnesses to the universe's first chapters. There are galaxies without dark matter, and we don't know why. Dark matter is supposed to be the invisible glue that binds galaxies together. It explains why stars move the way they do, why galaxies hold their shape, why clusters form giant webs across the cosmos. But recently, astronomers discovered something that shouldn't exist: galaxies that appear to contain little or no dark matter at all. In these strange galaxies, the stars orbit exactly as fast as expected from the visible mass alone, as if the hidden scaffolding is missing entirely. No one is sure how this is possible. Maybe past collisions stripped the dark matter away. Maybe these galaxies formed under unusual conditions. Or maybe our understanding of dark matter, its behavior, its identity, is still incomplete. These dark matterless galaxies are like quiet contradictions drifting through the cosmos, reminders that even our strongest theories may be only partly true. The sun rings like a giant booming bell. Deep inside the sun, pressure waves ripple through its plasma, bouncing from layer to layer, the way sound echoes inside a musical instrument. These waves are incredibly low in frequency, far below anything humans can hear, but they cause subtle vibrations across the sun's entire surface. With sensitive instruments, scientists can detect these ripples. By studying how the sun rings, they can map its interior, uncover hidden flows of hot gas, and measure the rotation of layers we can never see directly. This field is called helioseismology, the study of solar vibrations. And in this sense, the sun behaves like an enormous glowing bell, ancient, complex, and always humming. By listening to the sun, we learn not only its secrets, but also the secrets of countless stars scattered across the galaxy. Oh, galaxies follow filaments made of something we cannot see. The largest structures in the universe aren't made of stars or planets or even gas. They're shaped by dark matter, an invisible substance that forms vast filaments across the cosmos. Over billions of years, galaxies gather along these filaments like beads sliding along tensioned threads. The filaments stretch for hundreds of millions of light years, connecting enormous clusters together in a web of gravity and invisible mass. We can't see these dark threads directly, but we can praise them by watching how galaxies move, how they cluster, and how their light bends as it travels through the hidden structure. Between these filaments lie enormous cosmic voids, regions, almost entirely empty, silent pockets where galaxies are few and far between. The dark matter filaments act as the quiet framework of the universe, shaping everything we see, holding galaxies in place, guiding their growth and their motion. And yet, for all their importance, we still don't know what dark matter truly is. We only see its touch, never the thing itself. Space can stretch faster than the speed of light. In our everyday world, nothing is allowed to outrun a beam of light. But space itself plays by different rules. In the first sliver of a moment after the Big Bang, The fabric of the universe ballooned outward so quickly that distant regions drifted apart faster than light could ever hope to cross them. This wasn't movement through space. It was the expansion of space itself, a quiet stretching of the cosmic stage. Even now, when we observe faraway galaxies, they aren't racing through the universe at impossible speeds. Instead, the space between us and them is lengthening steadily, gently, endlessly. At great enough distances, this stretching becomes so strong that those galaxies recede faster than light, slipping forever beyond our reach. It isn't a violation of physics. It's simply how the universe breathes on scales far grander than anything we experience. Calm, relentless expansion, carrying everything with it. Sama Shipo. Our solar system moves through space like a helical spiral. We usually picture the planets circling the sun like clockwork gears, flat rings, smooth and predictable. But if you pull the camera back and watch the sun's path through the Milky Way, the picture transforms. The sun rushes around the galaxy at nearly 1 million kilometers per hour. As it moves, every planet follows behind it, spiraling in a twisting corkscrew path. Each orbit becomes a loop on a long, drifting ribbon. Not a flat diagram, but a flowing helix, a layered choreography of curves within curves. Everything in space is in motion, the planets around the sun around the galaxy around a larger cluster, and that cluster drifting through the expanding universe. Even now, as you rest, you're traveling through space in a slow, elegant spiral carried forward by motions so vast you never feel them. Janeo. Even nothing has a temperature. If you traveled far from every star past the last trails of dust into the deep intergalactic dark, you might think you'd find perfect emptiness. But the vacuum still carries a faint warmth. Its temperature, just 2.7 Kelvin, is a whisper of the universe's first light. The cosmic microwave background, stretched thin by billions of years of expansion, fills every corner of the cosmos. Wherever you go, it follows. A delicate thermal afterglow from a time when the universe was dense, bright, and impossibly young. As the universe continues to expand, this glow slowly cools. Trillions of years from now, it will drift closer to absolute zero, though it can never quite reach it. Even in the deepest void, the memory of heat remains. Quantum fluctuations may have shaped the entire universe. In the smallest, quietest layers of reality, the universe flickers. Energy appears and disappears in tiny bursts, brief, unpredictable tremors allowed by quantum uncertainty. According to many cosmologists, these minuscule fluctuations didn't stay small. During the universe's first heartbeat, a period of rapid inflation stretched space at staggering speed. And as space expanded, those tiny quantum ripples were magnified across the cosmos. They became seeds, seeds where matter gathered, where gravity pulled a little harder, where galaxies would one day ignite into spirals of starlight. The grand structure of the universe, clusters, filaments, voids, may all trace their origins back to ephemeral flickers at the smallest possible scale. Everything we see, from galaxies to the atoms in your body, may have begun as the soft trembling of nothing at all. Not all stars end with a bang. Some fade more gently, breathing their last in long, slow rhythms. In their final chapters, certain stars begin to swell and contract in repeating cycles, their brightness rising and falling like a soft pulse in the dark. These are variable stars, celestial pendulums, whose outer layers expand cool and then collapse again, heating as they tighten. Some complete this cycle in days. Others take months or even drift through these changes over years. For astronomers, these pulses have become cosmic rulers. Because a star's rhythm is tied to its true brightness, its heartbeat can reveal how far away it lies. But beyond their scientific value, these stars offer something quieter, a reminder that even as they dim, they keep their own time, slow, steady, and deeply ancient, breathing out the last echoes of their lives across the void. Across cosmic ages, Earth drifts inside a giant bubble of hot gas. If our eyes could see in ultraviolet and X ray light, we'd discover that our solar system isn't floating in ordinary space at all. It rests inside a vast, irregular cavity carved into the Milky Way, a glowing chamber called the local bubble. Stretching hundreds of light years in every direction, this bubble was likely sculpted millions of years ago by a chain of supernova explosions. Each blast pushed gas outward, heating and sweeping up material, carving out a great hollow in the interstellar medium. Today, our solar system simply glides through this low density pocket. We can't feel it, we can't see it, but it surrounds us like a silent room created by long extinguished stars, violence transformed into calm, a relic of ancient fire, now softened into emptiness. Oh, so there is a vast empty region hiding behind the Great Attractor. The Great Attractor is one of the strangest landmarks in the universe, a gravitational anomaly so massive that entire clusters of galaxies, including our own, are slowly drifting toward it. But what lies behind this immense concentration of matter is even stranger, a gigantic cosmic void called the dipole repeller. This region contains so few galaxies that its emptiness creates a kind of gravitational push, not by force, but by absence. Where matter is missing, space expands more freely, nudging galaxies outward. Together, the Great Attractor and the Dipole Repeller act like a cosmic tug of war, one drawing us in, the other gently urging us away. We are steered by both presence and emptiness, by gravity and by the lack of it. The universe guides us not only through what is there, but also through what isn't. Neutrinos pass silently through Earth and through you. Right now, without interruption, trillions of neutrinos are streaming through your body every second. They slip through your skin, your bones, the entire Earth beneath you, never slowing, never stopping. Produced in staggering numbers by the sun, by nuclear reactions, by supernovae, and even by the Big Bang itself, neutrinos are among the most elusive particles in existence. They carry no charge, almost no mass, and interact so rarely with matter that most will travel through light years of lead without touching a single atom. Deep underground enormous detectors wait for the rare neutrino that happens to collide with something, but the rest simply glide through space and matter like silent travelers that fill the universe even when everything seems perfectly still. The most massive stars can collapse directly into black holes without a sound. We imagine the deaths of giant stars as spectacular detonations, supernovae, that blaze brighter than entire galaxies. And often that's true. But for the heaviest stars, the ending can be startlingly quiet. When these giants exhaust their fuel, their cores collapse inward so violently that even the outer layers cannot resist. Instead of exploding, the entire star simply falls in on itself. No brilliant flash, no expanding cloud of gas, just a sudden disappearance as gravity overwhelms everything. This process, called direct collapse, creates a black hole in near silence, a hole punched into space time without the usual fireworks. A star that lived brightly for millions of years ends not with a roar, but with a quiet surrender to its own weight. In an instant, a star can simply wink out its light, fading forever as it collapses inward. What remains is a black hole, silent, hidden, unbearably dense. Astronomers have even watched stars that seem to vanish between observations as though someone dimmed the universe's lamp without warning. It's a soft reminder that not every ending flashes brightly. Some disappear the way a breath fades in cold air, quiet, sudden, and complete. Galaxies can orbit each other like moons circling planets. We often imagine galaxies as solitary spirals drifting alone through the cosmic sea, but the truth is far more social. Many galaxies gather in small groups, tugging on each other with gentle gravitational hands. Our own Milky Way is surrounded by dozens of companions, tiny satellite galaxies, moving along enormous slow arcs. Among them are the large and small Magellanic Clouds, drifting like glowing lanterns tethered to our galaxy by invisible threads. Over millions of years, these companions can be stretched into long ribbons of stars, twisting tidal tails that wrap across intergalactic space. Some small galaxies will eventually be absorbed, becoming part of the larger galaxy's glow. These dances are not fast. They are long, patient orbits, graceful partnerships unfolding over billions of years. Even galaxies in the quiet dark rarely drift alone. Look. The brightest explosions in the universe come from collapsing magnetic stars. Among the rarest and most violent events in the cosmos is something called a magnetar hypernova. A magnetar is already an extreme object, a neutron star with a magnetic field so intense it could erase a credit card from halfway to the moon. But if a massive star collapses and forms a magnetar that releases its energy all at once, the result is a burst of radiation more brilliant than a typical supernova. For a few heartbeats, it may outshine entire galaxies. Some of the longest gamma ray bursts, the universe's most energetic flashes, may come from these collapses. They last only seconds, but their light can travel billions of years to reach us. A tiny stellar core, wrapped in magnetic fury, collapsing into darkness. yet lighting the universe on its way down. The edge of the observable universe is not the edge of everything. When we gaze into deep space, we can only see so far, about 46 billion light years in every direction. That boundary isn't a wall. It's simply the limit of the light that has managed to reach us since the beginning. The universe almost certainly extends far beyond what we can observe. And because space is stretching faster and faster, many regions are racing away from us more quickly than light can cross the gap. Their light will never arrive. Not now, not ever. So the observable universe is like a glowing bubble centered around us, not because we are special, but because we can only see what has had time to appear. Beyond that bubble may lie uncountable galaxies, endless clusters, perhaps even endless space. A horizon, not an edge. Some galaxies launch jets of plasma that stretch for millions of light years. Deep in the centers of many galaxies sits a supermassive black hole. When gas and dust spiral toward it, the infalling material heats to incredible temperatures. But not all of it is swallowed. Some of this matter gets funneled along magnetic fields and blasted outward at nearly the speed of light, forming jets so powerful they can spear through intergalactic space for millions of light years. These jets glow in radio waves, X rays, and sometimes visible light. They can sculpt entire regions of space, compressing gas clouds, triggering star formation, or sweeping material aside like a cosmic wind. From a distance, they look like lighthouse beams, in the darkness, narrow focused, impossibly bright. A reminder that even in the presence of a black hole, some things escape. And when they do, they redraw the structure of the cosmos itself. Some of that falling material doesn't disappear at all. Instead, it spirals into tangled magnetic fields, gathers momentum, and is hurled outward as narrow jets, thin, focused streams of plasma accelerated to nearly the speed of light. These cosmic beams extend far beyond the galaxy that launches them, sometimes stretching across millions of light years. In radio wavelengths, they glow like immense ghostly pillars, marking their reach through intergalactic space. Galaxies powered by these engines are known as radio galaxies, home to some of the largest structures the universe can create. It's a quiet contradiction. The strongest outflows come from the neighborhood of black holes, places where light itself struggles to escape. Even silence, it seems, can carve its signature into the cosmos. So, there is a star in the Milky Way that orbits backward. Most stars move together in one grand rotation around the galactic center, following the Milky Way's spiral flow. But not every star follows the stream. One particular star, cataloged as H043539, travels the opposite way, drifting against the current like a lone swimmer moving upstream. Astronomers believe it may be a relic from another galaxy that once merged with our own, carrying its old orbit with it. Another possibility is a gravitational slingshot, an ancient encounter with a black hole or a dense cluster that flung it into reverse. Whatever its origin, this backward moving star is a reminder that even in a galaxy shaped by order and rotation, There are outliers tracing their own quiet paths through the dark. Thomas. The center of our galaxy contains molecules that smell like raspberries and rum. It sounds whimsical, but it comes straight from real chemistry. When astronomers studied a giant dust cloud near the Milky Way's core, they discovered ethyl formate, a molecule that on Earth gives raspberries their flavor and rum its sweet aroma. Of course, space doesn't smell the way air does. The vacuum can't carry scent. But the presence of such molecules reveals something deeper. Interstellar space is rich with complex organic chemistry. Inside those clouds are alcohols, simple sugars, and even precursors to amino acids. Not life itself, but the ingredients from which life could begin, floating silently, drifting between stars, waiting for worlds to form. So this it's some say it's some oh. A galaxy is headed toward us, and it's already touching ours. The Andromeda Galaxy, our nearest large neighbor, is slowly moving toward the Milky Way. Right now, it lies about 2.5 million light years away, but that distance is shrinking. In roughly 4 billion years, the two galaxies will begin to merge. Yet, in a way, the meeting has already started. The vast halos of gas and dark matter surrounding both galaxies overlap now, blending at their edges. The future collision won't be a violent smash. Stars are so far apart that most will slip past each other undisturbed. Over billions of years, the two spirals will swirl together, stretch, reshape, and eventually settle into a single enormous galaxy, an elliptical giant sometimes nicknamed Milk Dramita. It's a slow cosmic waltz already underway, unfolding in silence across unimaginable time. Oh, Vanam. The cosmic microwave background still glows around you, all around you, even here. In this quiet moment, there is an ancient light, a faint uniform glow that fills the universe in every direction. It's the cosmic microwave background, the leftover radiation from when the universe was only about 380,000 years old. Before that, the cosmos was a brilliant fog where light couldn't travel freely. But once atoms formed, the fog lifted, and that first light began its journey. Over billions of years, the expansion of space stretched it into cool microwaves. Now it drifts around us as a soft, invisible afterglow of creation, a whisper from the universe's earliest dawn. Wherever you go, that ancient light is there, too gently filling the cosmos with the memory of its beginning. It isn't something your eyes can catch or your skin can sense yet with the right instruments. This ancient glow appears a soft cosmic whisper from the universe's earliest years. This faint light is the oldest signal we can detect, a quiet memory from the universe's childhood, still drifting through space and time. Some supernovae are powered by collapse, not by light. We tend to imagine supernovae as blazing, radiant events, explosions so bright they outshine galaxies. But not every dying star goes out in a flash. Some massive stars experience what astronomers call a failed supernova. Their cores collapse directly into a black hole, and instead of erupting outward, the outer layers fall inward, vanishing into darkness without producing a visible burst. In rare observations, stars that once shone steadily have simply disappeared from the sky. No explosion, no lingering glow, just silence. These quiet endings reveal that some of the most violent processes in the cosmos unfold without light, hidden behind gravity's curtain. Bookis. Entire galaxies exist as dim shadows made mostly of gas and dark matter. When we picture galaxies, we think of bright spirals and glowing clusters of stars. But some galaxies hardly shine at all. These faint systems contain very few stars, yet they still hold enormous mass, mostly in cold gas and dark matter. They barely appear in telescopes, showing up only as soft smudges or through gravitational clues. Some may be galaxies that never manage to ignite many stars. Others may have lost their gas early in cosmic history or are passing through a temporary dormant phase. Their quiet presence reminds us not all galaxies blaze with starlight. Some drift almost unseen, shaped only by gravity and time.
Chatham.
Black holes can collide, merging in silent cosmic dances. When two black holes orbit one another, they slowly lose energy by releasing tiny ripples in space time gravitational waves. As this energy leaks away, the black holes spiral closer, circling faster and faster until they collide and merge into a single, larger black hole. There is no flash of light, no visible explosion, just a surge of gravitational waves spreading across the universe. In 2015, detectors on Earth recorded such a ripple for the first time, confirming a prediction Einstein made a century earlier. Since then, dozens more have been heard distant collisions from deep cosmic history. For a brief moment, the fabric of space itself vibrates, as if the universe were singing. Vo. Some stars die in slow motion, fading over billions of years. Not every star ends with a burst of light. Smaller stars, like our Sun, fade gently. After exhausting their hydrogen fuel, they expand into red giants and slowly release their outer layers into space. The core that remains becomes a white dwarf, a dense hot ember glowing with stored heat. A white dwarf doesn't shine because of fusion, it simply cools very gradually over billions of years. Eventually, it will become a black dwarf, cold, dark, and invisible. But the universe is not old enough yet for any white dwarf to have cooled that far. Everyone ever formed is still glowing faintly, somewhere, soft embers scattered across the galaxy. Their endings are not fireworks, but quiet fades into cosmic night. Just how it goes. Time slows dramatically near a black hole. Einstein's theory of relativity tells us that gravity shapes not only space, but time itself. The stronger the gravitational pull, the slower time passes. Near a black hole where gravity is extreme, time can nearly stop compared to regions far away. If you orbited close to the event horizon, minutes for you might correspond to years for someone on Earth. This isn't imagination, it's a measured effect called gravitational time dilation. We even correct for a mild version of it in the clocks aboard GPS satellites. Black holes don't just trap light, they stretch, twist, and reshape time. Shabmo. Oh. The emptiness between galaxies is colder than anything we can create on Earth. Venture far beyond stars, planets, or drifting gas clouds, and you reach the vast intergalactic voids regions where space is almost perfectly empty. There, the temperature falls to only a few degrees above absolute zero, about 2.7 Kelvin. This coldness comes from the cosmic microwave background, the faint glow of the early universe, still cooling as space expands. In those enormous stretches of near nothingness, heat has nowhere to linger. It's a cold deeper and quieter than any laboratory could ever reach. A chill so vast it fills the spaces between galaxies. That temperature is colder than anything on Earth, and even colder than what most laboratories can create. This deep chill comes from the near absence of particles or energy. There's nothing to hold warmth, just a few wandering atoms and the fading microwave afterglow of the early universe. These intergalactic voids are the quietest, most isolated regions we know, vast empty expanses stretching across millions of light years. They are the universe's deepest shadows, holding only the soft echo of creation. Uh, um, um, the universe is slowly becoming more transparent. In its earliest stage, the universe wasn't clear at all. Light couldn't travel freely because everything was wrapped in a hot, glowing plasma, a fog of electrons and atomic nuclei constantly scattering photons. As expansion cooled this cosmic fog, electrons finally joined nuclei, forming stable atoms. With that simple shift, light was suddenly free to move. This moment, called recombination, occurred about 380,000 years after the Big Bang and released the cosmic microwave background we still detect today. Since then, as galaxies formed and matter spread out, the universe has become clearer and clearer. There is less to block or scatter light, and more places where photons can travel undisturbed. A universe that once glowed like a dense fire has become a vast, transparent ocean of space. We have photographed the shadow of a black hole. In 2019, scientists with the Event Horizon Telescope revealed the first direct image of a black hole, or rather of its shadow. The black hole in galaxy M87, 53 million light years away, appears as a dark circle surrounded by a glowing ring of superheated gas twisted by gravity. No telescope sees the black hole itself, but the light around it is bent into a halo, outlining the place where nothing escapes. Capturing this image required a global network of synchronized telescopes working together as if Earth itself were one giant lens. It wasn't just a picture, it was a quiet scientific milestone, our first real glimpse into one of nature's most mysterious phenomena, seen not in theory, but in light. Important. You can see a galaxy with the naked eye from your backyard. Most galaxies lie far beyond what our eyes can detect. But one, the Andromeda Galaxy, is bright enough to see without a telescope. On a clear, dark night in the northern hemisphere, it appears as a faint, misty oval in the sky. That soft glow has traveled for over 5 million years before reaching your eye's light that began its journey long before humans existed. Andromeda contains more than 1 trillion stars and is slowly drifting toward the Milky Way. Yet from the ground, it's just a gentle smear of brightness on a dark canvas. It's astonishing. You can step outside, look up and see an entire galaxy with nothing but your own eyes. A tiny detector once captured the whisper of a distant black hole collision. In 2015, the LIGO Observatory detected something subtle yet extraordinary, a faint ripple in space-time itself. It came from two black holes merging over 1 billion light years away. The signal was unimaginably small, a distortion far tinier than the width of an atom, but it carried a story of massive objects spiraling together and colliding in perfect darkness. This detection confirmed Einstein's century old prediction and opened an entirely new way to study the universe, not through light, but through the tremors of space-time. A quiet whisper from the deep cosmos heard across 1 billion-year distance. These waves are unbelievably faint. By the time they wash across Earth, they stretch and squeeze space by an amount smaller than a single proton. Yet, with instruments built to sense the tiniest motion, we can still hear them. LIGO and its partner observatories work like enormous cosmic ears listening for the universe's softest tremors. Their first detection confirmed something Einstein predicted a century earlier, that even in the perfect quiet of space, colossal events can send vibrations across the cosmos. A single chirp born from two invisible giants spiraling together billions of years ago was caught by a small detector on a quiet blue planet drifting through the dark.
Chaikin.
Some regions of the universe are drifting away forever. The universe is expanding, and that expansion is accelerating. As space stretches faster and faster, some galaxies retreat so quickly that their light will never reach us. Even if we waited for eternity, the gap would widen too fast for their photons to cross. They've slipped beyond the cosmic event horizon, a one-way boundary set not by walls, but by the speed of space itself. Over billions of years, more and more of the universe will fade from view, not because those galaxies vanish, but because their light simply can't keep up. The cosmos isn't only growing, it is quietly letting parts of itself drift into permanent distance.
So to space. Vamos to assess our base of biggest
Some black holes may be older than the stars themselves. Most black holes form when massive stars collapse. But there's another stranger possibility: black holes born before stars even existed. These hypothetical objects, primordial black holes, may have formed from tiny fluctuations in the extremely dense, turbulent moments after the Big Bang. Regions where matter crowded together so tightly that gravity compressed it into microscopic black holes. Some could be tiny, smaller than mountains. Others might have grown over billions of years. We've never confirmed one, but if they do exist, they could explain dark matter, help seed early galaxies, or reveal secrets about the universe's first seconds. Ancient black holes, older than suns, older than galaxies, silent fossils from the dawn of time.
Subto enchikavunk.
Entangled particles may connect distant parts of the universe. Quantum entanglement is one of the strangest ideas in physics. When two particles become entangled, their properties stay linked even if they are separated by light years of space. Change one and the other responds instantly. This doesn't send information faster than light, but it hints that reality at the smallest scales is woven together in ways we don't fully understand. Some physicists suspect entanglement might even play a role in the structure of space-time itself, a hidden thread that helps stitch the universe together. If so, particles born in the earliest moments of creation could still be entangled today, their connections stretched across the vast expanding cosmos. An invisible network quietly linking corners of the universe that may never meet in any other way. If so, there may be quiet, invisible threads running through the cosmos, delicate quantum echoes from the universe's earliest moments, still lingering in the stillness between galaxies. Even in the vast emptiness, something faint and ancient may connect distant regions, a whisper from the dawn of time, woven into the fabric of space. The vacuum of space carries its own pressure. What we call empty space is anything but empty. Even when there are no particles, no atoms, no light, quantum physics tells us that the vacuum is alive with motion. Tiny flickers of energy appear and vanish. Particle antiparticle pairs bubble into existence and dissolve, and fields tremble at scales far smaller than atoms. This restless background creates what physicists call vacuum energy, a gentle, persistent pressure built into the very structure of space. On the largest scales, this pressure may explain dark energy, the mysterious force causing the universe to stretch faster and faster. Unlike ordinary energy, vacuum energy doesn't thin out as space expands. It stays constant, and the more space grows, the more vacuum there is, so the push becomes stronger. A strange truth emerges. The more nothing the universe creates, the more something arises to drive everything apart.
So.
Black holes glow with the faintest heat evaporating over unimaginable time. Though black holes are famous for their darkness, they are not completely silent. Stephen Hawking showed that quantum effects near the event horizon allow a tiny bit of energy to leak out as Hawking radiation. It works like this: virtual particle pairs form at the edge of the black hole. Normally, they annihilate instantly, but occasionally one particle falls in while the other escapes. The escaping particle becomes real energy. The black hole loses an infinitesimal amount of mass. Over staggeringly long periods, longer than the age of the universe multiplied by trillions upon trillions, a black hole can slowly shrink and eventually fade away entirely. No explosion, no dramatic flash, just an impossibly slow dimming, a final whisper into the dark.
Samso. Also stick all the go and say to separation pos equals us us but us or up.
Most matter in the universe isn't solid, it's plasma. When we think of matter, we picture everyday forms, solids, liquids, gases. But the universe mostly operates in a fourth state plasma. Plasma is a superheated ionized gas where electrons roam freely instead of staying bound to atoms. It fills stars, flows through the solar wind, moves between planets, drifts through galaxies, and dominates the enormous spaces between galaxy clusters. It behaves unlike anything we touch on Earth. Plasma dances along magnetic fields, carries electrical currents across light years, and creates the glowing structures we see in nebulae and auroras. Here on Earth, we only glimpse it in lightning flames or neon lights, but in the cosmos, plasma is everywhere, quietly shaping the luminous architecture of space. Gravitational waves move at the speed of light. Gravity is not only a force, it can ripple. When massive objects such as black holes or neutron stars collide, they send waves through space-time itself. These ripples stretch and compress the fabric of the universe as they sweep outward in all directions. And they travel at the speed of light, the absolute speed limit of the cosmos. It took decades of effort to build detectors sensitive enough to measure the tiny distortions these waves cause, changes smaller than the width of a proton. But now, from Earth, we can listen to collisions that happened billions of years ago. Each gravitational wave carries a signature: how heavy the objects were, how fast they spun, how violently space was twisted in their final moments. They are messengers from events we cannot see, a way for the universe to speak through motion rather than light. Gravitational waves are silent to our ears, yet they move through the universe with absolute certainty. They ripple gently through space-time, passing through stars, planets, and even our own bodies without making a sound. Tiny shudders in the deep structure of the cosmos, subtle reminders that the universe is always shifting, always whispering, even when everything feels still. The cosmic web connects galaxies across unimaginable distances. If you could map galaxies on the largest scales, you wouldn't see a chaotic scatter. You'd find an intricate network, an enormous lacework of filaments, and empty spaces stretching across billions of light years. This is the cosmic web, a sprawling pattern where galaxies collect along invisible strands of dark matter, like dewdrops along a spider's thread. At the intersections of those strands lie superclusters, massive knots of galaxies bound together by gravity. Between the filaments stretch enormous cosmic voids, regions so empty they feel almost like punctuation marks in the architecture of the universe. We can't view the entire web at once with any telescope, but when we stitch together large surveys of the sky, its shape reveals itself, not random, but organic, resembling branching roots, foaming patterns, or even the neural networks inside a brain. The universe on its grandest scales seems woven rather than built. The James Webb Space Telescope observes galaxies frozen in time. JWST was designed to look farther than any telescope before it, and by doing so, it peers deeper into the universe's past. Because light has a finite speed, the farther we look, the further back in time we see. Some galaxies Webb observes may no longer exist in the forms we see them now. They may have merged with neighbors faded away or transformed entirely over billions of years. But their ancient light is still traveling through space, still arriving at our detectors like delayed postcards from an era long gone. Astronomy is full of this quiet paradox. Nothing we see in the deep sky is happening now. Every image is a layered timeline of the universe's history, a mosaic of moments scattered across billions of years. Every deep field picture is also a time machine.
So the wall was a semesters.
Many galaxies shone with light older than the Earth itself. When you look at a galaxy billions of light years away, its glow began traveling through space long before our planet formed, before the sun existed, before any trace of life appeared in the cosmos. Some of the galaxies visible today emitted their light when the universe was young, over 10 billion years ago. That light has been stretched, cooled, and reshaped by expanding space, yet it still reaches us as a faint, patient whisper of what once was. The stars that produced that glow may be gone now. Their light remains carrying their memory across cosmic time. The night sky is full of ancient messages, older than Earth, older than the oceans, older than the idea of time as we know it.
So
Entire galaxies can hide behind curtains of cosmic dust. Even something as vast as a galaxy can vanish from view when masked by thick clouds of interstellar dust. These clouds aren't like household dust. They're made of microscopic grains of carbon ice and silicates drifting through frigid molecular clouds. Invisible light, they can completely obscure whatever lies behind them. But in infrared radio or X ray wavelengths, the hidden galaxies emerge glowing faintly behind the dust like lanterns behind fog. Astronomers have discovered whole galaxies this way, revealed only when viewed at the right wavelengths. Darkness, it turns out, doesn't always mean emptiness. Sometimes it simply means hidden. When some galaxies are surrounded by perfect rings of distorted light, when a massive galaxy sits in front of a distant source of light and the alignment is just right, gravity bends the background light into a glowing circle. This phenomenon is known as an Einstein ring, a beautiful halo created not by motion, but by the curvature of space-time itself. These rings may come from background galaxies, quasars, or even supernovae, whose light has been warped by the lensing galaxy. They're rare, delicate, and exquisitely symmetrical natural telescopes that help scientists measure mass map, dark matter, and study the early universe. They are illusions born from gravity, perfect circles shaped by the invisible geometry of space.
up
The universe itself may have no boundary at all. When you look up at the stars, it's natural to wonder where everything ends. But based on what we know, the universe may simply continue without limit, no edge, no wall, no outer surface. We can see only the portion of the cosmos whose light has had time to reach us, the observable universe. But beyond that horizon, space may stretch on indefinitely, perhaps forever. More galaxies, more stars, more silent reaches of space, continuing far beyond our sight. A universe without edges, only expanding possibilities. If the universe truly has no boundary, then most of its vastness will always remain beyond our reach. No matter how advanced our telescopes become, or how long we wait for light to arrive, enormous regions of space will continue moving away from us faster than their light can travel. Those places will never be visible, not because they disappear, but because the expansion of space pushes them beyond our horizon. An infinite universe doesn't necessarily promise infinite possibilities, but it does suggest an endless openness, a quiet immensity with no clear edge and no final limit. Cosmic rays constantly reach Earth from deep space. Every second, high energy particles arrive from the Sun, from distant stars, and from violent events scattered across the galaxy. Many come from exploding stars or energetic black holes accelerated to incredible speeds. Most of these particles are stopped by Earth's magnetic field or absorbed by the atmosphere, but a few reach the ground, and some even pass straight through your body without interaction. They're harmless in small amounts, yet each one carries a story that began far from Earth, a tiny fragment of a distant event making its way to our planet. The question, what happened before the Big Bang, feels natural, but it may not have an answer. According to many cosmological models, the Big Bang wasn't just the beginning of matter and energy, it was also the beginning of time itself. If time started at that moment, then asking what came before is like asking what lies north of the North Pole. Some theories propose earlier states of the universe or invoke quantum physics, where time behaves differently, but in most descriptions, the Big Bang marks the point where space and time emerge together. It wasn't an explosion inside an existing space, it was the origin of space. Quasars were once confused with faint stars. When astronomers first observed them, they looked like small, distant points of light, almost indistinguishable from ordinary stars. But their unusual spectra and unpredictable brightness made them stand out. It took years to understand that these objects were actually the extremely bright centers of distant galaxies powered by supermassive black holes consuming surrounding gas. The energy released in that process is so intense that it can outshine every star in the galaxy. Their light had been traveling for billions of years. Yet to early astronomers, they appeared as simple star-like dots in the sky. The Milky Way is also moving through space as part of a larger structure. Along with the Andromeda Galaxy and several dozen smaller companions, we form a collection called the Local Group. This entire group is drifting toward a region of strong gravitational influence known as the Great Attractor. And beyond that lies an even larger concentration of mass, including the Shapley supercluster. Much of this region is hidden behind the dense plane of our own galaxy, making it difficult to observe directly, but its gravitational pull is unmistakable. Our galaxy, along with its neighbors, is slowly moving towards something enormous and partly unseen, guided by forces that shape the motion of entire galaxy clusters. We still don't know exactly what lies in that direction, only that we're slowly drifting toward it, guided by the pull of enormous unseen structures. And while our galaxy makes its long migration, we find ourselves living in what many astronomers call the universe's stellar springtime. Today, the cosmos is filled with stars, forming, shining, and exploding, but it wasn't always this way. For hundreds of millions of years after the Big Bang, the universe was dark, without a single star to illuminate it. When the first stars finally ignited, they transformed everything, and star formation rose rapidly over cosmic time. It has since peaked and begun a slow decline, leaving us in a moment where stars still form regularly, though not as abundantly as before. One day, the very last star will be born. After that, the universe will gradually dim as existing stars age, burn out, and fade away. First, the massive blue giants will disappear, then stars like our sun, and finally, the small red dwarfs that can burn for trillions of years. The cosmos won't end. Suddenly, it will simply grow quieter, cooler, and darker as the ages pass. Most of the matter shaping this enormous system is invisible. The stars and galaxies we can see make up only a tiny fraction of what exists. The rest is something we call dark matter, a form of matter that doesn't glow or reflect light, but still exerts gravity. We know it's there because galaxies rotate faster than they should. Clusters of galaxies are held together more tightly than expected, and light bends more strongly when it passes through certain regions of space. All of this points to an unseen mass that outweighs normal matter by more than 5 to 1. Dark matter forms the hidden skeleton of the universe, an invisible structure guiding the formation and motion of galaxies while remaining forever out of sight. Even the light we receive from the earliest galaxies carries the imprint of time. As light travels through space, it doesn't remain the same. The expansion of the universe stretches those waves, shifting them toward the red end of the spectrum. Light that left the first galaxies billions of years ago began as bright visible starlight, but by the time it reaches us, it has stretched into the infrared. This stretching, called redshift, helps astronomers measure how far away something is and how long its light has been traveling. Thanks to telescopes like the James Webb Space Telescope, we can finally see this ancient softened light, a whisper from the young universe stretched by the slow expansion of space. Some physicists even wonder whether the universe itself is not quite what it seems. A concept known as the holographic principle suggests that everything in our three-dimensional reality may actually be encoded on a two-dimensional surface at a deeper level of physics. This idea comes from studies of black holes, where the information about everything that falls in seems to be stored not within the volume of the black hole, but on its surface. If this principle applies to the universe as a whole, then the world we experience might be a kind of projection, a real one, but rooted in a more fundamental layer of reality we cannot perceive directly. It's a strange possibility, but one that arises naturally from the mathematics of gravity and quantum theory. Some theories go even further and suggest that the entire universe might operate the same way, with what we perceive as space and depth emerging from information encoded on a distant boundary. If that's true, then the three-dimensional world we move through each day may be a kind of mathematical reconstruction, a smooth illusion built from something more fundamental. Nothing about this changes daily life. Of course, but it's a quiet reminder that reality, even when it feels solid, may hold deeper layers than we realize. Even the fabric of space may not be perfectly smooth. To our eyes and instruments, space looks continuous, but some models of quantum gravity predict that it could be granular at the smallest possible scale. This limit is known as the Planck length, around 10 to 35 meters, so small that no current tool can probe it. At that scale, space-time might break into tiny units of foamy texture underlying everything. If this idea is correct, then stars, galaxies, thoughts, and even the act of falling asleep all take place not in a flawless void, but on a foundation built from invisible, fundamental quanta. Among the strangest objects that inhabit this universe are stars that spin faster than kitchen blenders. Some stars rotate so quickly that their equators bulge outward, their shapes distorted by their own speed. Neutron stars take this even further. Millisecond pulsars, dense remnants of collapsed stars, can rotate hundreds of times per second, meaning a city sized sphere of supercompressed matter is spinning faster than a blender blade. Their beams of radiation sweep through space with incredible precision, making them some of the universe's most reliable natural clocks. When cosmologists consider the fate of the universe, the leading picture is not a sudden collapse, but a long, gradual fading. Galaxies drift apart, star formation slows, and one by one, the existing stars exhaust their fuel. Black holes slowly evaporate. Over unimaginable stretches of time, matter itself may decay, and the cosmos becomes colder and emptier. This final state is known as heat death, an end not of fire or destruction, but of silence, where energy is spread so thin that nothing new can form. The universe began quietly, and eventually it may fade just as quietly. Yet even now, galaxies can reshape themselves through immense forces. At the centers of some powerful winds push outward, driven by supernova radiation and the intense activity around supermassive black holes. These galactic superwinds can carry gas dust and even young stars tens of thousands of light years into intergalactic space. Over time, they can strip a galaxy of the material needed to create new stars, gradually shifting it into a quieter, redder system. These winds also distribute heavy elements into the cosmic web, spreading the ingredients for future planets and life. In a way, a galaxy breathes drawing matter inward, igniting it, and eventually exhaling it back into the void. Far in the future, the cosmos will become something like an endless dark ocean. Galaxies will drift so far apart that each will stand alone in the blackness. New stars will no longer form, and even the faint embers of white dwarfs will cool into darkness. Only scattered remnants will persist, black holes slowly evaporating and particles drifting through cold, empty space. This is the ultimate quiet of heat. Death, not a dramatic ending, but a vast stillness without motion or warmth. And here in the present, we might already be living inside a region of unusual emptiness. The universe is laced with great walls and filaments of galaxies separated by immense voids, expanses stretching hundreds of millions of light years, with very little matter inside. Some scientists believe our location may lie within one of these underdense regions. If that's true, it could help explain subtle features in the cosmic microwave background and the measured rate of cosmic expansion. It doesn't change our day to day experience, but it hints that our cosmic neighborhood might be quieter and emptier than most. Living inside a cosmic void doesn't affect our everyday experience, but it does shift our place within the larger structure of the universe. What feels like ordinary emptiness may actually be the quiet center of a vast, underdense bubble, one pocket within a sprawling cosmic web shaped by invisible gravity. We drift through this region without noticing it carried gently along by the deeper currents of large scale structure. Among the universe's most intense objects are magnetars, neutron stars, whose magnetic fields are trillions of times stronger than Earth's. A magnetar is small, only the size of a city, yet its magnetic force is powerful enough to distort atomic structures, erase data across enormous distances, and tear matter apart. These magnetic fields fade with time, but while they exist, they unleash flares and bursts of radiation so powerful that even a distant eruption can be detected from Earth. No laboratory could ever recreate such intensity. Magnetars are quiet, dense remnants of collapsed stars, objects made of pressure memory and magnetism existing at the extreme edge of physical possibility. On far larger scales, the universe holds structures that challenge our expectations. In 2013, astronomers discovered an enormous collection of quasars, a large quasar group stretching more than 4 billion light years across. Each quasar is the bright, active core of a distant galaxy, and together they form a pattern so vast it may exceed what our cosmological theories predict. The universe is supposed to become smooth at sufficiently large scales with no structures beyond a certain size. Yet this quasar grouping appears to push past that boundary. Whether it represents a real physical structure or simply an unusual statistical clustering is still debated. Either way, it reminds us that the universe often reveals more complexity and connection than our models anticipate. At the other end of the scale lie black holes where gravity curves space and time into a narrow one-way funnel. Approaching a black hole means entering a region where time slows dramatically for an outside observer. Space folds inward, and the event horizon marks the border beyond which all paths lead toward the singularity. Near this boundary, the distinction between space and time blurs, falling inward, becomes less a direction in space and more a direction in time itself. Isn't a metaphor, but the actual geometry of space-time shaped by extreme gravity. Because the universe is expanding and its expansion is accelerating, some regions are already receding from us faster than light can travel. Their light will never reach us, no matter how long we wait, and messages sent in their direction will never arrive. As time passes, more and more of the universe will drift permanently out of contact. Eventually, each galaxy or small group of galaxies will exist as an isolated island surrounded by deepening darkness. Not because the universe shrank, but because space expanded faster than light could bridge the distance. a quiet separation written into the long future of cosmic evolution. This doesn't break any law of physics. Nothing is actually moving through space faster than light. Instead, space itself expands calmly, silently, and without resistance, gently pushing distant regions of the cosmos apart forever. It's not motion, it's growth, a quiet rearranging of distance that slowly changes what parts of the universe can ever communicate again. The heaviest element forged in a star's explosion is gold, and its story is far more violent than its beauty suggests. Gold can't be made in the hearts of ordinary stars. It forms only in the universe's most extreme collisions, when neutron stars crash together or in rare, powerful supernovae. In those moments, matter is squeezed and shattered, with unimaginable force, and heavy elements like gold, platinum, and uranium are born. Over time, those atoms drift into gas clouds, become part of new stars and planets, and eventually settle into rings, jewelry dust, and circuitry. Every piece of gold you've ever touched carries the memory of a stellar catastrophe, a quiet fragment of an ancient cosmic fire. As light travels from distant galaxies, it moves through space that is stretching beneath it. The light keeps racing forward at the speed of light, but the fabric it crosses is expanding. That expansion stretches the light's wavelength, pulling it toward the red end of the spectrum. This cosmological redshift isn't the light slowing down or losing energy by collision. It's simply the signature of a universe growing larger as the signal travels. When we look at faraway galaxies, we see not only their age and distance, we see how space has changed since their light began its journey. A silent record of the universe's steady breathing written into every photon. Long before the universe became transparent, before atoms formed and light could travel freely, the cosmos was a hot, dense plasma. In that early sea of particles, pressure and gravity created oscillations, ripples, that behaved very much like sound waves. These waves left a permanent imprint on the distribution of matter, like the echo of a ringing chord that never fully faded. Today, we can detect that ancient pattern as a slight preference in the spacing of galaxies, a frozen memory called baryon acoustic oscillation. It's a fossil of cosmic sound, preserved across billions of years, a quiet ripple that helped shape the grand structure of the universe. Galaxies themselves also reveal how the cosmos grows and changes. Sometimes, a smaller galaxy drifts too close to a larger one and is slowly torn apart. Its stars stretch into long streams, dissolve into the larger galaxy's halo, and eventually blend so completely that the original system disappears. The Milky Way bears the scars of these feasts, faint stellar streams looping across the sky, the remnants of long lost companions. Galactic cannibalism sounds violent, but in reality it is slow, graceful, and inevitable, a quiet folding of one galaxy into another over billions of years. And then there are stars that flicker like fireflies scattered across the night. Not every star shines with steady light. Some pulse softly, dimming and brightening in rhythmic patterns caused by internal pressure waves, surface activity, or eclipsing companions. These variable stars blink with cosmic regularity, some over hours, others over months or years. Their steady rhythms make them natural clocks of the universe, tools astronomers use to measure cosmic distances. But even without their scientific value, there's something gently soothing about the idea stars breathing in slow celestial patterns, shimmering softly across time. This doesn't break the laws of physics. Nothing is actually outrunning light. Instead, it's the fabric of space itself that expands steady quiet and unstoppable, gently stretching the distances between galaxies until some regions drift beyond one another forever. Gold, the heaviest element we commonly encounter, has an origin far more dramatic than most people realize. It isn't produced in the cores of ordinary stars. Instead, it's forged only in the most extreme environments the universe can offer when neutron stars collide, or when certain rare types of supernova explode with unbelievable force. In those brief moments, atomic nuclei are crushed together under intense heat and pressure, creating heavy elements like gold, platinum, and uranium. Then these atoms are blown out into space, mixing with drifting gas and dust, eventually becoming part of new stars, new planets, and even the objects we wear or hold. Every gold ring, every tiny grain of gold in Earth's crust began as debris from a cosmic explosion, a small reminder that the universe creates beauty through fire. As light travels from distant galaxies, it moves through space that is gradually expanding. So when we observe that ancient light, we're not seeing only the galaxy as it looked long ago, we're also seeing how the universe changed while the light was on its way. As space stretches, the light stretches too, its wavelength lengthening and shifting toward the red. This cosmological redshift doesn't come from collisions or slowing down. It's simply the effect of space getting bigger while the signal travels. Faraway galaxies are therefore more than distant. They are witnesses of how the cosmos has breathed and expanded across billions of years. Long before space cleared enough for light to move freely, the early universe was a dense glowing plasma. In that hot mixture of particles, pressure, and gravity produced oscillations, compressions, and expansions that behaved almost like sound waves. When atoms finally formed and light could travel, these ancient sound waves left a subtle pattern frozen into the distribution of matter. Today, we can detect this imprint in the spacing of galaxies, a faint echo known as baryon acoustic oscillation. It's a fossil of cosmic sound, a gentle ripple from a time before the universe became transparent, still shaping the large scale structure we observe today. Galaxies, too, leave traces of their long histories. Over billions of years, they interact, collide, and sometimes consume one another completely. When a small galaxy wanders too close to a larger one, gravity can slowly tear it apart. Its stars stretch into thin, glowing streams, merging into the bigger galaxy's halo until the smaller system disappears entirely. Around the Milky Way, we've identified these remnants arcing streams that were once separate galaxies. This quiet process called galactic cannibalism isn't violent. It's gradual, graceful, and one of the main ways large galaxies grow over time. And scattered across the sky are stars that don't shine steadily at all. Some of them flicker bright and dim, and pulse with remarkable regularity. These variable stars change because of pressure waves inside their core's eruptions on their surfaces, or because a companion star briefly blocks their light. From Earth, they appear to blink gently, like celestial fireflies drifting through the dark. Their rhythms are so consistent that astronomers use them as tools to measure distance across the universe. What seems like a soft flicker in the night sky is actually a precise and dependable clock marking time on a cosmic scale. Supernova remnants are the slow afterbreaths of long dead stars, expanding clouds of gas and dust still drifting outward long after the initial explosion's light has disappeared. Even after a star's final flash, its remains continue to move through space like a fading echo carrying clues about the life it once lived. Light itself can also be reshaped in surprising ways. We usually imagine only massive objects, stars, black holes, entire galaxies bending the path of starlight. But even something as small as a planet has enough gravity to warp the light passing near it. When a planet drifts exactly between a distant star and our viewpoint on Earth, its gravity can briefly magnify and distort that distant glow. This phenomenon, called microlensing, is subtle and fleeting, but powerful enough to reveal planets we would never be able to see directly, even those in other galaxies. A tiny rise in brightness, a gentle curve in a star's light, and suddenly a hidden world makes itself known. The planet may be cold, dark, and invisible, but the bent starlight is enough to whisper, I exist. In the very young universe, everything looked different. Instead of the dark sky we know today, the cosmos once glowed with a warm orange light. In the first few 100,000 years after the Big Bang, space was filled with a dense, brilliant plasma. As the universe expanded and cooled to roughly 3000 Kelvin, the first atoms formed and allowed light to travel freely. In that moment, the entire sky would have appeared softly illuminated, an orange radiance stretching in every direction. Over billions of years, that glow was stretched by the expanding universe into the faint microwave background we can detect today. But long ago, all of space shimmered with a gentle amber hue, a final warm flare, as the cosmos began to open and grow. As the universe ages, it cools overall, but not every region cools at the same pace. Expansion reduces temperature gradually, yet dense regions full of gas galaxies or trapped radiation hold onto heat far longer. Massive galaxy clusters, for example, contain hot gas that remains warm for billions of years. Meanwhile, emptier regions cool much more quickly. These subtle temperature differences shape how cosmic structures form, how stars evolve, and how long certain environments remain active. The universe doesn't cool like a machine lowering its power. It cools like weather, a patchy, uneven landscape with warm pockets, slow fades, and quiet variations across space. And then there is an idea more speculative, but deeply intriguing, the possibility that new universes could emerge from our own. Some cosmological theories propose that under extreme conditions, perhaps inside black holes or through rare quantum events, entire new regions of spacetime might bud off, creating separate universes with their own laws of physics. If such an event happened far from us, we might never detect it directly. But in theory, we could one day observe hints, an expanding bubble of unfamiliar physics forming somewhere beyond our reach, marking the birth of a new cosmos. A new universe beginning its own story while ours continues to unfold. We don't know whether a new universe has ever budded off from our own. We don't know if it ever will. But the idea lingers quiet patient that somewhere in the deep darkness, the cosmos could one day give rise to something new, a beginning unfolding inside an ending, a soft whisper forming inside a silence so large we can barely imagine it. The universe itself still carries the marks of its earliest moments. In the tiny sliver of time, right after the Big Bang, everything expanded extraordinarily fast, an event known as inflation. That sudden surge stretched quantum fluctuations across space, turning microscopic ripples into the seeds of all future structure. Galaxies, stars, planets, all of them trace their origins back to those first trembling patterns. The echoes of that moment are still here. We see them in the faint temperature variations of the cosmic microwave background, and someday we may detect them as primordial gravitational waves. Subtle ancient vibrations still traveling through space-time. The universe may seem calm now, but it still hums with the memory of its own birth, like a bell quietly resonating long after the initial strike. And in the middle of all that immensity, there is you, a way for the universe to become aware of itself. Every element that makes up your body was forged in the heart of stars. The carbon you breathe, the calcium in your bones, the iron flowing through your blood, they were created in cosmic furnaces, scattered through space and woven into life. You are not separate from the universe. You are a small, bright moment of it made conscious, a flicker of awareness in a cosmos that otherwise simply expands, collapses, glows, and grows cold. Through you, the universe sees. Through you, it wonders. Through you, it dreams. As we drift together toward the end of tonight's journey, thank you for spending these quiet moments exploring with me. We've moved across vast distances, past collapsing stars and newly forming galaxies. We've listened for the faint ripples of space-time and followed the traces of the oldest light ever released. And in the middle of all that cosmic motion, there was you breathing gently, your thoughts softening, maybe already sinking into sleep. The universe is full of energy and motion, but it also holds places of deep stillness. It contains fire and gravity, but also peace, soft, steady, lingering. And the fact that we can sit with it like this, piece by piece, in calm and quiet reflection, is something truly beautiful. So, wherever you are now, whether your eyes are still open or drifting closed, may your dreams be soft. May your body settle like starlight on calm water. And may you carry with you, even faintly, the memory of a universe that glows not only above you, but within you. If you're still awake, you're welcome to continue on to the next chapter. And if you'd like more journeys told softly, more stories of space to fall asleep, to feel free to subscribe. There's always more to explore, slowly, gently, one sleepy soul at a time. Good night.